Hello, welcome to the Area Research Committee webinar on the subject of the 6th research project. This is Christine Perret. I'm here today to host this webinar. It's a member exclusive webinar, so I'm going to be skipping my normal presentation about the area's ecosystem goals and members and proceed directly to telling you a little bit about the research committee's structure for these projects. I'd like to remind everybody that you are in listen-only mode. You can put questions into the question panel of your GoToWebinar application, and we will be taking those questions at the end of this, after the presentations. Would you please move to the next slide? So just to remind everybody that we are talking about the 6th in a series of research projects, you can move to the next slide, that we've been conducting on behalf of area members. And the way we go about doing this is we ask members to submit topics, ideas, pain points, anything that they would like to have a research project focusing on. Then we have a ballot, and through a democratic process, we choose one of the ideas submitted. Then this cycle happens twice a year, and the area dues pay for the hiring of a research team. And then we manage that process through to the completion of the project. At the end of the project, there's almost always a report, or to date, there has always been a report. And if you could go to the next slide, I'll explain that each project has got a different topic. So we've learned that it's valuable to have some kind of a tool that accompanies the report. We like for the reports to be actionable, and the tool helps to make that come to life in a way. So as you can see on slide 4 here, we have been conducting 2 of these per year, and this is the web-based AR and Enterprise project, which we we hired Brainwave and partners to conduct. So this is the concluding webinar about this project, and we expect to have the report out to you in a few weeks. We didn't want to delay in getting this, this information to our members now. At this time, I'd like to ask to go to the next slide and invite Tony Hodgson and Phil Lamb to share with us what they've learned and the next steps. What does the future look like for web-based AR in the enterprise? Thank you, Tony. Welcome.
Great, thank you very much, Christine. We really appreciate this opportunity and look forward to reporting on what we found and taking questions. My name's Tony Hodgson. I'm CEO of Brainwave LLC. We're a global consulting firm in emerging technology, augmented reality, virtual reality, and artificial intelligence. We're members of the area and have been pretty much since the inception, and we've been the chair of the security committee for the area for quite some time now. Phil, I'll let you introduce yourself, please, sir.
Thanks, Tony. So my name's Philip Lamb. I'm in the Emerging Technologies Division at Mozilla. Of course, Mozilla is a global organization that's most well known for our suite of browser products. And Mozilla conducts a number of projects in forward-looking research, and our mixed reality program is included in this.
You'll be hearing more about that in just a bit. We also have 2 other parties which were members of our research study team for this project. The Georgia Tech Augmented Environments Lab, that's led by Blair McIntyre, participated, and also Alfred University in New York, and Dr. John Simmons, the Executive Director of Research and Economic Development, was a participant, and is also on this call. The key deliverables as part of this study were twofold. One was a written report, which, as Christine explained, you'll see distributed in its final form in the next couple weeks, and it explains our extensive research on the topic at hand, and we identified key industry players and organizations. We discussed the results of a survey and of multiple interviews that we conducted with area members and industry stakeholders. We present our key findings, and we provide a detailed list of resources that you can refer to later regarding WebAR. Secondly, we developed a working WebAR enterprise implementation prototype using WebAR, which you'll see a little bit later this morning. Phil's going to show it. And this prototype simulates an elementary field service application. We'll be making that working code and the documentation publicly available in the coming days. Phil, I'll turn it over to you now to explain a little bit more about Mozilla, please.
Thanks, Tony. So a reasonable question to ask is why a company better known for web browsers is involved in mixed reality research. And the answer's for the same reason that many of you are here. The future of interfaces in the digital world is already evolving. As a company involved in user agency and interfaces to the web, we see a good match between the Mozilla mission and the needs of mixed reality users. We refer to this program as mixed reality. It covers the full spectrum of augmented and virtual reality applications. The open standards-based platform of the web has the ability to address many of the problems that mixed reality developers and users face. And our research program addresses this through a kind of comprehensive coverage of 4 different areas. And the user agency, we realize that access to a full suite of browsers is important. And so we try to be present on every one of the mixed reality platforms there. 3D content needs to be easy to bring to the web, so frameworks and tooling is a critical piece, and really our participation in this project is focused on that area. Collaboration in these areas is where the rubber hits the road, actually. And the true value of where the web part of the platform comes into play. And standards and advocacy is a critical area, as we've learned in the past, and we've focused in this project and in other areas on standards-based approaches. Next slide, please, Tony. So one of our positions, which you'll hear from me and others at Mozilla, is that developers are being put in a difficult position right now. The same kind of proliferation is occurring in augmented and virtual reality application development environments that occurred in the past in other types of media on the web. There's a proliferation of platform and delivery mechanisms that are not necessarily serving users' interests. Next slide, please, Tony. Of course, the risks, things we need to consider. There are platform lock-in risks and diversification to counter these risks, fragmentation. Certainly App Store models are not necessarily at all easier for enterprises than they are for the independent developer. You might be a competitor to the App Store provider, or your content is counter to their brand, and so they can yank the rug out from underneath you if you encroach on things like profit streams, or if you try to build in networking or social features that conflict with their platform provided ones, or even in-app commerce. And investing in a platform and then finding out that it has significant privacy and security holes is a major risk. Next slide, please, Tony. So the Mozilla approach is to avoid both proprietary platforms and walled gardens, and to adopt a standards-based platform where there are multiple vendors. So most developers have existing web-based content pipelines and web development teams. It makes far more sense to extend those pipelines and skills to a new application domain than it does to make a large investment in new tooling that you can't easily pivot away from. So the web platform, of course, has particularly strong benefits in areas of interest to enterprise. Not having to deploy apps to devices enables centralized deployment and control of the user experience. On security, the app user is the beneficiary, and the browser makes an explicit contract between the web application and the user's data. So when you consider things like an AR platform that's using cameras all the time, it's important for the user to be able to trust that the data that's being processed by the platform is being used only for the purposes of enabling that experience and not being subverted and sent somewhere else. So a user of a web AR or VR application can be more confident that information about their workplace environment, for example, is not being sent in raw form to the application provider. More confident than a similar user of a native application, we believe. And of course, standards radically reduce the risk of unplanned lock-in or obsolescence. I'll hand it back to Tony for the next piece.
Great, thank you very much, Phil. I appreciate it. So what we know is that augmented reality has already well proven its value in enterprise environments, and we see scores of examples with very healthy return on investments, and more of those seem to show up weekly. But there are still challenges to the widespread adoption and proliferation. First of all, the complexity and expense of programming and maintaining proprietary native AR application solutions, the lack of operating system interoperability and device portability for sharing content, and poor integration with existing extensive web infrastructure and tools and applications and data that people have already invested in. So for example, Microsoft HoloLens and Magic Leap are extraordinary solutions and systems for AR, but they are expensive systems, and the app development for those is relatively complex. The content can't be ported easily from one solution to another solution. The App Store distribution model is cumbersome and requires the user to search for, download, install, and then configure applications before they can actually view and use them. And then they can't readily share those with other people. So in order to proliferate, we believe a new paradigm is required for enterprise AR, and we are not certainly the only ones who feel that way. Fortunately, an exciting alternatives emerging that addresses these challenges, and it's known variously as web-based AR or web AR or the immersive web. And this is a new paradigm that allows creation and delivery of AR experiences using the web development protocols and tools and viewing using common web browsers, which enables essentially instantaneous delivery to any smartphone, tablet, or AR, VR headset with a single code base that you access by just going to a URL. So additionally, what is distinct but intimately related with this concept of web-based AR is the driver of the whole thing, which is being driven by the World Wide Web Consortium and creation of a new mobile device API specification that's referred to as WebXR. So when we say WebXR, we're talking about the W3C spec and then the broader context of where that's being applied and the other technologies that are being used to deliver web-based AR. We just, in this report, and often are calling just web AR. So the W3C, as many of you probably are aware, is the same international standards body that promulgates other web specifications like HTML and cascading style sheets and JavaScript. And the WebXR spec provides an advanced interface between browsers and mobile devices, including smartphones, tablets, and AR headsets, which allows a deeper level of access to the device resources like user input data, sensor and display information, and it overcomes the limitation of the native app approach, which allows viewing of the AR content in the browser and seamless access and sharing of the content using common hyperlinks. The Immersive Web Working Group and the Companion Community Group were founded in 2017, and they're led by development engineers from nearly every major browser vendor, most notably Mozilla, Samsung, Google, and Microsoft, not to leave anyone out. There are about 250 individuals who are officially registered in the group, but there are really about 20 organizations that regularly participate and contribute. The first working draft of WebXR was released in October of 2019, and it provides for basic VR capabilities across these devices. And today, the specification's been extended out to also include basic AR capabilities, namely the ability to position 3D experiences in scenes and make those scenes relative to the floor or the ground. Soon, additional functionality is going to follow. So to be able to put AR experiences referencing tabletops and vertical surfaces, and then additional functionality. And then there's sort of a special emphasis and conversation going on about security and privacy. So the question might come to mind, why should you care? There seem to be three different major stakeholder teams that are stakeholder groups that really have a vested interest in WebAR. First of all, for app developers and system integrators, this provides an easy way to create and maintain applications for your clients using a single code base. For the end users, it's of easy and familiar access that they already use on a daily basis, but now they can also get access to these AR and VR experiences on any device. And for enterprise managers, the key stakeholders here at the area, this is going to allow you to save time and money on your AR experience development solutions by leveraging your existing investments in your development teams and in your web resources that you already have going on. So when we look around, we see that the ecosystem around WebAR is beginning to take shape. We have the Immersive Web Working Group, as we've discussed, that's driving the standard. We have browser vendors that are adopting this standard and progressively adding functionality to their various versions of their browsers. We also have key WebXR frameworks that have been developed to assist companies with developing their solution. And then there's a host of companies, some of them who've been around for quite some time, and then some emerging companies and offerings that are focused on these interoperable web-based solutions. This table shows compliance of the various browsers with the WebXR standard. And since the situation's progressively changing, this may already be out of date. And so this gets updated on a regular basis. As part of this research study, our team conducted a survey between March 4th and March 22nd of this year. We asked 13 questions regarding users' knowledge of and experience with AR and with WebAR specifically. And then we had 4 questions on demographics. We had 95 people that answered some or all of the questions, and they represented nearly 20 different industry segments. So that was a pretty good broad group of participants. Over 2/3 of these participants were either very or extremely familiar with augmented reality, and 1/3 of them were at least basically aware of WebXR. There were only 8% that had actually deployed web-based solutions at this point, and those are basic solutions. But 2/3 of those who were aware of WebXR are planning to deploy within the next year. So this is good news, like signals some rapid adoption potential here. The primary interest that they indicated in WebAR is the accessibility for the end user and the number of end users that you can reach with your code base. Also noted was the ability of existing resources and the ease of deployment of these solutions. The main concerns about WebAR as the architecture of choice were about the lack of availability of development tools and an understanding really of what the specific performance capabilities are and will be for WebXR. So we've already discussed many of the strengths of WebXR. I'm not going to repeat those, but some of the key weaknesses or challenges to be addressed include the requirement that the system maintain network connectivity, right? And there are some ways that you could potentially get around that, but that connectivity also has to offer sufficient bandwidth and data throughput, which is currently improving with the rollout of 5G and Wi-Fi 6. Also, like other standards, collaboration on the WebXR spec is slower than the pace of commercial proprietary developments in the marketplace. So where can WebAR be put to best use in the enterprise? Our research indicates that it's great for initial pilot projects where you need to rapidly and inexpensively develop a prototype solution and demonstrate the basic value of AR for a use case. It's great where one can integrate with existing web apps and resources. So if you already have web applications for your employees and your workers, then adding this AR capability to that is a logical thing to do. Also, training was very often mentioned, and a lot of that, and for other reasons, the concept of product visualization, being able to visualize 3D models and 3D products was really prominent, especially as that supports training and both online and in-store sales and customer education. So also then several times in interviews, people reference that WebAR is going to be great for what we just put in a term, informed reality situations where the user just needs to quickly reference information and then move on to their next task. That would be prohibitive for having to go to an app store and download a new app or access one app and then switch from that app to another. The primary barriers that still remain in order for WebXR to proliferate include a lack of software development kits and tools for creation of the AR experiences, a lack of ubiquitous high-speed network connectivity that we discussed, and a slow pace of development of the WebXR spec and the functionality. And similar to native experiences, privacy and security are always a concern, and we're not saying that it's not sufficient, but it has to be understood, and we as an industry have to communicate that and understand it in order to have it proliferate. The bottom line factors that influence whether one elects to develop using either native AR or web AR experiences for the enterprise include that native apps are still better at performing. Generally, they have closer access to the processor on the device and graphics rendering capabilities, although that's being addressed. They're superior in their ability to integrate spatial awareness and object and feature recognition and tracking. That is also, people are working on addressing that with the web version. And typically with a native app, you can create some really complex and large experiences, and people have experience doing that, and so it's at a great state right now. We're not pretending that native applications are going away anytime soon or ever. There will always be a use for those likely. But for WebAR, this is just easier to create and maintain. You can reach a broad audience on various devices, and it's more cost effective than the native app approach. So to conclude, the research bottom line has convinced us and determined that WebAR is now a viable alternative for development of some enterprise AR applications, and it's growing in functionality to the point that because of its superiority in certain use cases, it's going to rapidly become the predominant paradigm in terms of number of experiences and how people access them for the enterprise. And there's a growing need for tools to help easily develop and discover and manage and integrate and share these web AR experiences. Phil, I'm going to turn it back over to you now and let you talk more about our enterprise implementation.
Thank you, Tony. So you've heard Tony discuss a number of things that are relevant in the current state of the art, particularly to the enterprise use. So I'd like to dive in at the start and get down to some specifics for technical considerations that we've been working to address. And some of the criticisms leveled at web-based applications is that they require porting effort and that they're lower performance. And so I would say in the past, those were both valid criticisms, but it's not necessarily the case anymore. And the big game changer has been WebAssembly, a Mozilla-founded technology platform for native code execution that has been taken up by all the browser vendors now. We're all familiar with JavaScript for client-side code execution. So WebAssembly extends that model, allowing native code to be compiled to a highly optimized bytecode, which then gets translated to native CPU instructions at runtime. This process is exactly how languages like Java and C# work, which of course power major computing platforms. Because WebAssembly integrates with the existing JavaScript virtual machine, we can access all the existing web APIs and even provide one-to-one implementations of existing native APIs like OpenGLES using a corresponding web API like WebGL. So therefore, a number of performance benchmarks and performance, it continues to be a strong focus for this work, but 70 to 95% of native performance on compute-oriented benchmarks is certainly a very compelling performance level for this kind of work. Next slide, please, Tony. So the building for WebAssembly is for many pieces of code no different from adding an extra compilation target to existing development pipeline. So a typical pipeline builds with a tool set like Emscripten that provides a tool chain that in turn uses Clang as the language parsing front end, and then LLVM to compile a bytecode. So these are large open source projects in themselves that drive the default compilation pipelines for most software development right now. So the linking step also adds glue code consisting of JavaScript and an optional hosting HTML page to load the WebAssembly code. And these files then are bundled up, served by a web server to a client device where the JavaScript and WebAssembly execute and the HTML content is displayed in the document object model. And next slide, please, Tony. So of course, you've heard Tony already mention the other key technology for AR and VR is the API via which we communicate with the hardware platform. I won't go into too much detail about WebXR at a strategic level, but it is a multi-vendor standard and that gives it a strength. The WebXR core device API was completed late last year. The gamepad module, December 2019. And the first augmented reality modules for HIT testing and DOM overlays are currently in prototype and review phase under the W3C process. There's a pipeline, of course, to address all of the current platform features that are available on devices and to ensure that they are exposed in an appropriate way. Next slide, please. So to provide both a platform for development and a proof of concept for this approach in a scientific and engineering context, we decided to port a large C++ code base and use it in interactive immersive media. For this project, I selected OpenSceneGraph. It's a project with a long development history, a large, highly optimized code base, and good documentation. Porting effort of this code base to WebAssembly was actually very low, meaning it was easy. And I got the core libraries at around 50% of the plugins compiling within under a day's work. Additionally, I ported a plugin to support GLTF model format, which is a W3C-backed standard for exchange of OpenGL compatible models on the web. So there is also a new development by the OSG project team named Vulkan SceneGraph, which is based on Vulkan, the successor to OpenGL in terms of graphics API. I'm looking forward to porting that to the web once we have a corresponding piece that we currently need, which is the successor to the WebGL API in the browser named WebGPU, which is currently under development and nearing completion for the first step. Next slide, please. If we also consider the pipeline for the 3D assets, we have to bear in mind, of course, that real-time rendering has quite different rendering demands from typical formats that might emerge from CAD or other enterprise modeling processes. For this project to cater to devices including low-end mobile hardware, fairly aggressively downsampled the models. And an automated pipeline can be built around tools like the OSG conversion tool, which is part of the OpenSceneGraph utilities, or there are a variety of other different tools that can be built into pipelines like this. We converted to a web-optimized delivery format, GLTF binary, and these are then packaged as part of the WebAssembly build. I'll talk more about other alternatives later to this pipeline. Next slide, please. So we've compared and contrasted web-based deployment of AR applications to native applications. So I think it's instructive to consider the application architecture that we get if we apply these tools. First, let's consider the default native app case. So augmented and virtual reality applications are not standalone pieces of code that communicate directly with hardware. In fact, they depend on several layers of technology, often including an app engine and a rendering framework, graphics API, a VR or AR system runtime, and platform APIs for other hardware access. We can represent the totality of the app and the underlying system on which it runs in an architectural stack diagram, where each layer depends on the layer below. So you'll see displayed here a representation of such a system running a contemporary virtual reality application. And some salient points in the native application: the unique portion of the app itself often consists of a relatively small amount of compiled and interpreted code, which is represented here in a blue tone. Almost always the bulk of the application, both in terms of delivery and lines of code, is some kind of third-party application engine, which is, in the VR case, often a game engine. And this usually includes a script interpreter. The app is also often coded in a language that runs in a virtual machine, for example, C# or a Java bytecode interpreter. Even compiled code such as C++ or Swift also depends on a runtime, although in those cases the runtime is usually part of the application rather than the operating system. And of course, the operating system abstracts its hardware through a variety of APIs, particularly relevant to VR and AR graphics and VR, AR hardware positioning APIs. Next slide, please. Now, if we consider the web-based application running inside a modern browser, the system architecture looks something like this. It is remarkably similar, and at the OS and hardware level, it's identical. So in the web application, The app, it still consists of compiled WebAssembly and interpreted script code, but application scripts are now first-class citizens in the system, and no in-process interpreter is necessary for them. Whereas in the native application, the app binds directly to the operating system level APIs. In the web version, the same capabilities are re-exposed in a standardized form by the browser, for example, Firefox. So we have this intermediate layer. A drawback of standardization is, of course, that the developer no longer needs to write. I'm just looking at my notes here. The app developer no longer needs to write different versions of the application to handle operating system differences. The app coded to these standardized APIs runs in any browser, but a drawback of standardization is that the platform may have some unique features that aren't immediately available to the developer. So to counter this, key web application APIs can include per platform extensions. And these are being developed for the WebXR specification. Of course, other key APIs such as web graphics APIs are by design very closely related to their operating system level counterparts, which makes porting of graphics code to JavaScript and WebAssembly uncomplicated. And the component inside the browser that ties the upper and lower layers together is the JavaScript and WebAssembly virtual machine. All application logic passes through this layer, so its performance is critical. Note, however, that any cost imposed by this layer is not only an extra cost to web applications, C# and Java applications that you would commonly use on Windows or Android, for example, also run in virtual machines. Next slide, please. So of course, that gives us a huge potential scope for a demonstration of this kind of technology. So we focused on three achievable goals. Firstly, to demonstrate the use of native rendering framework with WebXR. Secondly, to port a large performance critical C++ code base to the web. And thirdly, to connect with a web-based administrative interface. That should say connect to the interactive parts with a web-based administrative interface. So I have made the source code for this application, which I'll discuss over the next few slides, available now. You can go to this URL and access that anytime. Next slide, please. So we based this demo on a scenario of a field service worker. The logic here being that service tasks are centrally assigned using a conventional web front end. Service tasks are created in the system and assigned to a specific worker and involve the worker logging in on their AR device, choosing one of the assigned service tasks, and then in the field identifying that particular machine, stepping through the service task, which ideally would be viewed overlaid on the machine. So in this interface, you can see it can be customized with different sets of machines, workers, and assigned tasks depending on their role. Next slide, please. So the current state of supported device landscape is quite variable right now, but we expect this to continue to consolidate over the next few months. Most current in-market devices have a WebXR capable browser, and AR support's making its way into the WebXR spec and those browsers. WebAssembly is also well supported. Right now, the prototype demonstrator also depends on multi-threading support in WebAssembly, which limits our options right at the moment somewhat. Although there's a big ongoing project in all browsers right now, so we can expect to see this support change rapidly over the coming months. So just to call out a couple of things from the table, at present for this demonstration, the only devices category that has 3 green ticks there in the AR device list is AR Core powered Android phones and tablets. The constraint, of course, being the multi-threaded WebAssembly. VR devices support is across the board more comprehensive right now, and that just reflects the state of the relative development timelines of VR and AR browsers. So I'd like to jump right into a video of the demonstration. I'm going to introduce here. This is running on a handheld Android device using an AR mode. So let's roll the video. So at the start, the user taps the screen. They see a 2D web page interface here and choose an assigned worker and their task. They have to excuse that during the pandemic lockdown, this is recorded in my dining room, which is not ideal for an application that's designed to be real world scale and with large industrial machines. But you'll be able to run this directly from the website and try it out yourself in your own space. So, of course, we're displaying the machines in a pre-assigned virtual space here, overlaid, of course, on top of the actual space. And of course, the frame rate is interactive if you're actually not streaming it over the web. So I invite you to please try it out. So the user in each case is able to interact directly with the device to select the augmentations and to view the task. It's a bit easier to see actually in the next demonstration. So that's an augmented mode. We've also got a demonstration of it in a virtual reality mode, which is perhaps slightly more compelling. Let's roll the video on that one. And of course, you see a web browser interface. This is displayed in Firefox Reality, which is a Mozilla-based browser for virtual reality devices. And this is a typical workflow for immersive web, that the seamless mixing of virtual and 2D spaces with this enter and exit immersive workflow. So in this case, the user has a handheld controller. They're able to point at the machines and get details, find out which one is the correct one for the service task. So in this case, it's the bin mixer. The service task is displayed attached to the machine. And the user here is just clicking through to step through the list of task steps. All right, that concludes the video sequence. Let's go to the next slide. So reasonably brief, I do invite you to please try it out, the URL of the previous slide. And it should be obvious that there are a number of current technical challenges. While we've met the goals of combining a large C++ code base with immersive presentation in a web application, there are still many challenges to deploying this on a real world task right now. Firstly, we're in a kind of uncanny valley right at the moment in terms of technical support in the platform, where we're using features in the code base which are slowly filtering into actual browser implementations across the various platforms at a variable rate. Particularly multi-threaded WebAssembly support that I mentioned is tied to changes in the security model in the browser in response to the Spectre exploit. So these on the mobile and standalone platforms, are the slowest to attain the security patches that are necessary to use this kind of complex multi-threading in this case, but we expect that to change over the coming months, as I said. Secondly, in this particular application, we've not yet implemented runtime fetching of the model data. The model data is consumed on the native side of this WebAssembly code base. This requires a little bit of interop between WebAssembly and the browser for it to be these models to be fetched at runtime, which is not difficult, but it's not yet complete in this application. And another issue is that while the scene understanding is part of the native platform capabilities on these platforms, or at least a rudimentary form of scene understanding, when we move to an environment like the web, where potentially arbitrary applications can execute in the browser, we need a very tight focus on user data protection. So it's taking some time to move these advanced vision features into the WebXR specification. That work's underway though, so we expect to see fairly large jumps in the capabilities of the WebXR API over the coming months. The initial AR features of head testing and spatial anchors will certainly change the way that we can deploy this kind of application. So if we think about the broader questions of technical pieces required for web-based AR applications to become the de facto standard, there are some big opportunities here to disrupt the current model. Particularly, we currently have a reasonably unhealthy dependence on a single vendor for over 90% of our AR and VR applications. And this dependence also ties us to the game engine development model, since that's what's driving revenues in this space. It's fair to say that we lack a cohesive authoring environment for mixed reality web applications. So I would characterize this as an opportunity for AR to become an extension of existing tool sets currently in use in enterprise for building management, enterprise resource planning, maintenance and asset management, for example. But there are many other tool sets that we have out there that are applied that you can imagine that deployment of interactive applications would tie in well with. So there are a number of potential direct follow-on opportunities for area members to pick up and work with and build upon the code in the prototype. One immediate opportunity is to move from the demonstration scene with its arbitrary layout to direct integration with real machinery. And this will depend on some or all of the spatial anchors to make the application site aware, model-based tracking to allow augmentations to be visually registered to the actual machine, and semantic scene processing to allow for automated guidance of the user. All of these are under development in the specification and expect to see these emerging in browsers over the coming months. A second opportunity for members is to build out the real-time multi-user capability of the application. Synchronization of the scene graph across multiple users is not technically difficult and would open up the possibility of a desktop-based supervisory console display or additional participants and real-time participants in a given task. So tied to this requirement is the need to persist certain state across users. And this is a natural fit for tying the application state back into existing systems like process management, so that we have a virtual version of the classical mimic boards, for example. That concludes my presentation on the technical parts of this demonstration application. So I believe we're going to open up to questions and answers now.
Thank you, Phil, and thank you, Tony. That was excellent. Really learned a lot, and I think this is going to be valuable to area members. I had one question that I don't think you developed. What about companies that currently have applications written for native platforms? Are they going to need to rewrite or import, or how do they change their code so that it is compatible with the WebXR browsers? Either one of you, I'm not sure who can best answer that, but basically, what do developers need to do?
Yeah, I can certainly pick up on that. So hopefully, by taking a look at the source code for this demonstration, it should provide some reassurance that having a path for existing native code bases to be used without having to completely reauthor from scratch does away with the need to do significant porting efforts that would be typical to do interactive work in a browser. So, of course, there's still some development required, some porting effort, but these would be focused more on the user interface and not necessarily on the interactive pieces. So, I think we've seen some pretty substantial projects brought to the web through this kind of approach. I mentioned game engines, and these are drivers of things in interactive media. But for example, the Unreal engine, has been ported in this way and runs in the browser. So there are varying levels of integration. You can go right from a tight integration between the document object model that exists in a web page with certain small or high performance pieces written in native code and running through WebAssembly, or it can be a wholesale conversion where what you're essentially running is basically a mobile application that runs entirely in the WebAssembly process, and you just interact directly with its output. We think that the biggest benefit will come from the mixed model, because of course the web browsers and the web enables the abstraction of things that are in applications through a document object model enables accessibility and a variety of other features that are interesting and useful for these cases.
But we don't know of any tools today that would automate that process, or like you could do a recompile, like you could go back to the original project and recompile it, and it would, from a game engine environment to a web app.
Well, actually, yes. So for example, a lot of these development environments include some form of web export for applications now. For example, there's the Unity development platform has a web exporter. Some of these are not web enabled. Mozilla, for example, has we've published an export plugin for Unity, which allows a Unity web application to be WebXR enabled. So there are direct porting tools. Yeah, but equally well, if a straight mobile application could be ported, one that's not tightly tied to specific platform features, but deals with input and output in a generic way.
Okay. There's a question about the choice of Open Scene Graph. The prototype that you've developed as part of this project uses that library. Would it be possible to make the same models and the same logic run on a different native library? And what are the pros and cons of other libraries you could have chosen?
That's a great question. It's not tied at all to Open Scene Graph. There are equally well many other graphics frameworks. Obviously, rendering is a key interactive part that's high performance, which is why it's interesting for a demonstration of this kind of technology to focus on rendering. But equally well, we could have substituted other types of application processing in there. There are many, in fact, I think most web-based AR that includes a computer vision portion at the moment. Also uses the Scripton and WebAssembly toolchain, for example. Lots of them are based on the OpenCV computer vision library, running in this using the same kind of model. The thing that made OpenSceneGraph usable, even though it's reasonably long in the tooth as in terms of a code base, is that it's direct use of OpenGL, which is a very close cousin of the WebGL specification. As we see the Web GPU standards start to reach maturity and become available in web browsers, then other graphics libraries would be a better fit for that model. But certainly, OpenSceneGraph is pretty widely used in scientific and engineering context today, so it's a good fit there.
Yeah, I wanted to add, when you were talking about the model transmissions and so forth, you mentioned GLTF. I wanted to clarify that that's a Khronos group specification supported in the W3C WebXR, but it is a Khronos spec. Okay, so maybe this is for you and or Tony, it doesn't matter, but the models that were chosen as part of this this prototype, this demonstrator, they were fairly simple, but many of the enterprise use cases require complex CAD models. Are there some guidelines that you would give for using those CAD models on the web to either decimate or what are we going to do for that? Is that going to be a concern for people using WebXR?
That's also a great question. As you could see in the video sequences, which probably don't really do the interactivity of the application justice, we stripped models back to a reasonably low polygon count, and that's just to deal practically with a possibly large range of devices that people might want to test this out on. We're talking about a range from handheld mobile devices right up to desktop class computing platforms. So it's not necessarily that they have to be low polygon count. One of the constraints in dealing with models in this way is not necessarily polygon count either. Even interpreted environments, the polygons themselves are sent to the GPU on the device, whether that's sent from a web page or sent from a native application. So focusing on lower polygon count models for this demonstrator is more about memory usage on lower powered handheld devices. So it could be optimized if you have a particular application and a particular computing platform in mind. Equally well, that is a valid concern that in order to deal with really high-end models with potentially millions of parts, each of which might have very detailed 3D models. So the approach that Mozilla and others are championing in this area is really about cloud-based approaches where some processing happens in a GPU running in some form of local or remote cloud, and then areas of interest to the scene are streamed from that cloud-based GPU to the client device. And of course, there's some latency involved in this kind of streaming, but the streaming can be not just final pixels, but it can be intermediate stages of processing.
Sure.
For example, selection of model parts, or it could be it can be interactive pixels, and then we use feed forward processes to counteract for rapid head motion and other things, so that we mask some of that latency. But these are emerging approaches here, and Mozilla and Google and others are working on these as interesting research problems and practical applications in this area.
Well, thank you very much. If there aren't any other questions, I think that we should conclude today's webinar. Thank you, Tony and Phil, for this great project. We look forward to seeing the final deliverables and distributing them to our members over the next couple of weeks. Thank you, everybody, and have a nice day.
Thank you
Thank
very
you.
much, Christine. Appreciate it. Thank you, Phil.
Bye.